Hello everyone, I am Liza Verma, one of the assigned TAs of Microprocessors and Microcontrollers course taught by Professor Shantanu, and I'll be taking your weekly interactive sessions, and we'll be discussing some of the topics that were discussed in that week's lectures, and then we'll go on to solve some of the problem questions that will help you gain some insights or help you solve your actual assignments of the course. Right, so beginning with the session with the summary of this week's lectures. Yes, so starting with the number systems, I think number systems are fairly discussed in digital electronics also, but since we are learning them here just for the sake of recap, let's see what number systems are. So if I write a number 137 of what we know or how we generally use numbers, this number 137 would be in base 10. That means this number actually contains 100, 3 tens, and 7 ones, which actually adds up to 137 as we know it. So yeah, which means the leftmost, the rightmost digit would have a weight of 1, the digit next to it would have a weight of 10, the next one would have weight of 10 to power 2, and if we had another digit here next to 1, that would have a weight of 10 to power 3. So yeah, this is how a number system with base 10 would be. Similar for any other number system with say base n. If I have some number 1, 3, 5, 8 in some base n, so in base n means the rightmost digit would have weight of 1, next one would have weight of n, next one would have weight of n square, and this one will have weight of n cube. One more thing, the digit or bit with the weight of 1 is called least significant bit, and the other extreme bit is called maximum significant bit, LSB and MSB as we know it, right? So this number would actually in our the way we intuitively understand numbers would be 8 times 1 plus 5 times n plus 3 times n square plus 1 times n cube, right? So this is a number system, and the number system with base n. So we can call it base or radix, doesn't matter. Next thing would be digits or symbols. So what are the, if I say a number system with general base n, what would be the number of digits that it can represent, or number of symbols that can be used in that number system to represent a number? So that will be, let's take the same example. If I want to represent 137 in base, or let's just take a general case. If we have a number system with base n, right? So what will be the number of symbols that this number system can use to represent a number? That is the question, right? So let's take example of a decimal number system only with the base 10. So in a number system with base 10, how many symbols do we have to represent a number? Let's say we have 0, we have 1, we have, let's say, to 9. Now after 9, if I want to represent a number which is obviously 10, it requires two digits, two symbols that are already in our set of symbols, right? Which means these are the 0 to 9 are only the symbols that can be used in this number system with base 10. After 9, all of the numbers can be represented using various combinations of these 10 symbols, right? So for a number system with base 10, we'll have 10 symbols with value of the symbol with maximum value equal to 9, right? So for a general case of a number system with base n, the value will be maximum will be n minus 1, and the number of symbols will be n only, and symbols will be starting from 0, 1, 2 up till n minus 1, right? So these are the digits and symbols that can be used. Now next thing is conversion. How do you convert number representation between one number system to another number system? So let's say let's take the same example. If I want to represent 137 in octal number system with base 8 to a number system with base 5, how would you do it? So the general procedure is to convert this number to base 10 first and then convert it into desired number system, right? So let's convert this one to base 10. This will be 137 in 8 is 1 times 8 square plus 3 times 8 plus 7, which is 64 plus 24 plus 7 is 95 in decimal number system. Now to convert this to number system 5, what we'll have to do, we take the number, repeatedly divided by 5, and keep track of quotients and remainders, right? So 95 divided by 5 would be 1. So 95 divided by 5 would be 1 and 9, and remainder will be 0. Again divided by 5, dividing by 5 will have 3 and remainder will be 4. Again dividing by 5, quotient will be 0 and remainder will be 3. And the way we represent the number is taking remainders as the bits and taking them in upper direction. So the number would be 3 first, 4 next, and 0 next. So this is the representation of 137 in octal number system to a number in a number in a number system with base 5, right? So this is 340. Okay, this is the conversion. Now one important rule of conversion between number system with powers of with bases in power of 2, like if you want to convert from base 2 to power 3 to base 2 to power 2. Now if the number systems, the two number system that you want to convert your number into and from into will be we follow a general procedure. Let's say now 2 to power 3 is 8, 2 to power 2 is 4, which means you want to convert a number that is in base 8 to a number that is in base 4. So how do you do it? Let's say we want to convert a number 3, 4, 6, which is in base 8 to a number system in of base 4. So what do? The journal procedure is to convert this number into binary, right? So you convert this 3 into binary with binary, but also in the number of digits would be the number of bits will be 3, that is this power. For example, if you want to represent 3 in binary here, 3 can be represented by 2 and 1. 1 can represent 3, but here we'll take the number of bits to represent 3 would be 3, because 8 is 2 to the power 3. So this power will dictate the number of bits that you can use to represent this number into binary. So to represent 4, this is 3, 4 will be 1 0 0, this is 4, and 6 would be 1 1 0 6. So this is the representation of 346 in base 8 to binary. So to convert this to a number system with base 4, we'll have to make pairs. Now for converting a number from base 8 to binary, we made pairs of 3. Now to convert it back to a number system with base 4, that is 2 to the power 2, we'll have to make pairs of 2, because the power here is 2. So the pairs will be like this. And since this one is left here alone, we can add 0, doesn't matter, and this will make another pair. So what is this pair in binary converted back to? 1 0 is 2, 0 1 is 1, 1 0 is 2, 1 1 is 3, 0 0 is 0. So we get a number 3 2 1 2 and 4 base. So yeah, this covers our conversion from one number system to another number system. The whole magnitude bits string or array. Right. So how do you do it? Let's say I want to represent minus 13. We'll write magnitude of this number. Magnitude of minus 13 is 30. We'll represent it in binary. In binary it will be 8, 4, 0 and 1, 13, right? So this is the magnitude of the number. To represent minus 13, what you'll do is add one bit to the leftmost side, right? Or to be fair, I'll just leave it blank. For signed magnitude numbers, you will add one bit to the leftmost side depending on the sign of the number. Let's say I want to represent 13 only in signed magnitude representation. So in signed magnitude representation, you cannot write 13 as 1101, right? This is for unsigned representation. For signed representation, you will have to add one more bit representing only the sign of the number. For positive numbers, the bit will be 0. For negative numbers, the bit will be 1. So this bit what bit you are going to add depends on the sign of the actual number. So if I want to write minus 13 in signed magnitude representation, I would write it as 11101. 1101 being its magnitude and this one representing only the sign of the number. Now if I wanted to represent plus 13 in signed magnitude representation, we would have to write it as 0, 1, 1, 0, 1. This being the magnitude and this being the sign of the number. So whenever we do questions, it is already, if the signed numbers are being used, the representation will be mentioned. Normally if it's not mentioned, you take it 2's complement, but if it's mentioned that the numbers are represented in signed magnitude representation or 1's complement, or even if it's mentioned 2's complement, you take accordingly, take the numbers accordingly, right? So signed magnitude representation is easy. I think it's clear. Let's move on to next one. That is 1's complement representation. Yes. So starting with the 1's complement representation. 1's complement. Let's take same example, minus 13 only. If I want to represent this number minus 13 by 1's complement representation, what we'll have to do, normally you take 1's complement, take 1's complement of positive signed magnitude representation of the number, which means if you want to represent minus 13, you'll have to take 1's complement of the positive number in signed magnitude representation. If I want to represent minus 13, I'll represent first plus 13 in signed magnitude, write this in signed magnitude, which will be 0, 1, 1, 0, 1, right? And you take 1's complement of this number. So that will be 1, 0, 0, 1, 0. Now this gives you 1's complement representation of minus 13. So to take 1's complement, just there are 2 steps only. Write the positive of that number in signed magnitude representation and then take its 1's complement, right? So Yeah, I think this is clear. Next is 2's complement representation. Similar thing. Let's take same example again. If you want to represent minus 13 by 2's complement, write this number's positive form in sign magnitude. Write plus 13 in signed magnitude. That will be 01101, right? So now we'll take the 2's complement of this number. 2's complement will be, first take 1's complement. 1's complement is 10010. Then take 2's complement by adding 1. That will be 11001. Now this is the 2's complement representation of minus 13. Now we know how to write minus 13 in all three representations. Let's write them. Minus 13 in sign magnitude, 1's complement, 2's complement. In sign magnitude it is 11101, right? In 1's complement it was what, 10010, and in 2's complement it is 10011, right? So this is how you write a number in any of the three representation. Now the question arises here is, why do we need 2's complement? We need 2's complement because in 1's complement representation we get two representations for 0. Like normally how would you represent 0? 0 is 000. Let's say we are taking 4 bits. In 1's complement, if we take 1's complement, that will be 1111, which means in 0 will be represented by 1111 as well as 0000, but there is no minus 0, right? 0 is just 0, it cannot be positive or negative. So to address this problem, we use 2's complement method. So for 2's complement method, if you take 2's complement of this, you just add 1 to this 1's complement of 0. This will give us 0000, and 1 carry will take care of this later, but the end result is actually equal to the 0 that we started with. So since 2's complement representation addresses this problem, all the microprocessors, microcontrollers use 2's complement representation method to represent negative numbers, right? So yes, next thing that sir briefly discussed in lectures was the digital logic circuits. We all know logic circuits are taken digital input or analog input, which they recognize as high bit or low bit, and give output as well in zeros or 1 high bit or low. So I think this is well covered in classes, and we don't need to discuss this in much depth. So logical circuits, we all know AND gates, OR gates, NOT gates, XOR, XNOR. Realization of circuits can also be done, and one of the examples given in class was adder circuit, adder, half adder, and full adder. And realizations using Carnot maps was also discussed. Now adder was also discussed, and I'm not going to get into it. It was fairly discussed. Now what was not discussed was subtractors, so I thought we can do that. So yeah, subtractor, just like adder only, subtractor can be a half adder, a half subtractor, or full subtractor. So similar to the adder, we have two outputs, difference and borrow. In adder we had sum and carry, here we have difference and borrow. And to understand how, let's say first start with half subtractor. So similar to a normal subtraction, 0 minus 0 would be 0, there won't be any borrow. 1 minus 0 would also be would give a difference of 1, and there won't be any borrow. 1 minus 1 is also easy, 0, and there's no borrow. 0 minus 1 would give a difference of 1 and 1 borrow. Actually this is minus, and that's why we have a borrow. So let's say, yeah, so 1 minus 1, if inputs are a and b, so here by convention you take a minus b. A minus b means 0 minus 0 would give difference of 0 and borrow of 0, just like here. 0 minus 1 would give us difference of 1 and borrow of 1. Then we have 1 minus 0, which is difference of 1 and borrow of 0. 1 minus 1, 0, 0. Easy. Next we have full subtractor. Yeah, so what do we do here? We first do this operation, a minus b. Let's say the output is y. Then we do this output of a minus b and subtract it from borrow in. And whatever is the output from this operation will give us the actual output of the subtractor, right? So let's see some of the examples how it's done. Let's start with first one. A minus b is 0 minus 0, which is 0, and subtracted again by borrow in, we get 0 difference and 0 borrow. A minus b is 0 minus 0, so output is 0. 0 minus 1 will be difference of 1, just as here. 0 minus 1 is difference of 1, borrow of 1, difference of 1, borrow of 1. Next, 0 minus 1 is difference of 1, borrow of 1. What is the output? 1, right? And there's a borrow of 1 also, because so 1 minus 0 will be difference of 1 again, right? Output of 0 minus 1 is 0 minus 1 is minus 1, which means there's a difference of 1 and there's a borrow of 1 as well. So borrow of 1, difference of 1. 0 minus 1, 0 minus 1 is difference of 1 and borrow, let's take care of it later. 0 minus 1 is 1 and 1 minus 1 is 0. There is a difference, right? And since there was borrow here we get 1 borrow. Next one, 1 minus 0 is difference of 1, and that 1 minus 0 will give us difference of 1 and borrow of 0, right? So 1 minus 0 is 1. 1 minus 0 is 1. Again this b in is 1. You again subtract it by 1. You get 0. 0 difference and yes, 0 difference and 0 borrow. 1 minus 1 is 0. 0 minus 0 is 0 and 0. For this last row, 1 minus 1 is 0. 0 minus 1 is 1 difference and 1 borrow, right? So that completes our full subtractor. Next are sequential circuits. I guess sequential circuits, just like adder, subtractor and everything, were discussed fairly, and we'll be doing questions on sequential circuits, so I'm going to skip these. Memory interfacing, we are going to do questions regarding these also. We all know what RAM is, ROM is. Memory folding was fairly explained in the lecture by sir. Sequence of instruction implementation. So every instruction has three parts of its implementation. First is fetching, then is decoding, then is execution. So first instruction is fetched, then it's decoded by the decoder and the microprocessor, and then the instruction is executed, whatever the operation was there, like for example add or move b to b comma a. First the instruction is fetched, it is decoded what operation is to be done, and then once the microprocessor decodes what operation is to be done, it executes that operation, right? So yeah, this is what we were supposed to cover for the summary. Next we'll move on to the practice problems. Okay, so first of the question, yes, so first question is find 87.50 minus 45.75 using 2's complement arithmetic method. So here are two numbers that we are supposed to find this result of this subtraction and give it in terms of binary, right? So 87.50, and since the base is not given, it is natural to take it as 10. So let's convert 87.50 in base 10 to binary string. So how do you convert it? 87.50 will be, let's see, 87, okay. $87.50 will be, first of all, since it's a positive number, I'll add a 0 for its sign. Then it will have 164, right? 032, 116, 08, 14, 12, 11 plus 0.5. 0.5 is represented by 1, 0, right? 0.5 is in 10 can be represented by, since the weights here are 2 to power minus 1, 2 to power minus 2 in binary, and so the decimal part, how do you convert it into binary? Let's say 0.5, you multiply it by 2, what you'll get is 1.0. Okay, so you write it as 0.0 and the digit before the decimal is taken out, and since 0 times 2 is again going to give us 0, we won't take more multiplication steps. and the digits here are taken downward as opposed to the previous uh, for the number before decimal, right? So 0.5 is written as 1 only, and 87.50 is represented by this array of strings in binary, right? So how do you represent 45.75? First of all, what is 45.75 in the sign magnitude representation of 45.75? 45.75 in sign magnitude. For positive, first bit will be 0, and how many bits are represented? 1, 2, 3, 4, 5, 6, 7. We'll have to represent 45 by 7 bits, but since there is no 64 bit is 0, there will be 132, 0, 16, 1, 8, 1, 4, 0, 2, and 1, 1. Point. Now how do you represent 0.75? You multiply it by 2, right? So what is 1.75.2? It will be 1.5. So you take the digit before decimal outside 1, and we remain with 0.5, right? Multiply it again by 2, you get 1, like 1 here and 0.0 here, and we take it downwards. So 0.75 is represented by 0.11 in binary. So this is sign magnitude representation of 45.75. Now taking since we are asked to do it by 2's complement arithmetic method, we'll write minus 45.75 by 2's complement method. And to do that, what do we need to do? Take 1's complement first of sign magnitude representation. Now how do you do that? 1's complement will be 1, 1, 0, 1, 0, 0, 1, 0.00, right? This is 1's complement representation of 45.75. This is first step. Second step is to add 1 to this to get 2's complement representation. This will be 1, 0.01001011. This is 2's complement representation of minus 45.75. Now to get this operation done, what we need to do now is to add this and 2's complement representation of this negative number. So let's do that. 0, 1, 0, 1, 0, 1, 1, 1.1. This is 87.50, and this is minus 45.75 plus. This will be 1, 1, 0, 1, 0, 0, 1, 0.01, right? We'll add these 1, 1.1. Now 1 plus 1 would give us 0 and carry of 1. 1 plus 1 again 0, carry of 1. This will be 1, 1 plus 1, 0, carry of 1. Again 1 plus 1 would give us 0, carry of 1, 1 plus 1, 0, carry of 1. So this is your number, right? So, and if we want to check what is the actual, what does it actually represent, let's convert it back to a decimal number system number. So this will be 0.11 we already know is 0.75. This is 1 plus 8, 9 plus 32. Yes, 9 plus 32 is 41. 41.75 in, and let's see what 87.50 minus 45.75 is. 0.75. These two match up, so our answer is correct. This is just a proof check. So what is this string corresponding to the options? Oh, only one of them has MSB as 0, so yeah, A is the correct option. I hope the solution was clear. Let's move on to the next question. Yes. So which of the following bit patterns results in this given string when added to 610? So we are given 4 option of bit patterns, and we are asked which one of them will result in this bit pattern when added to this. So one of these when added to 6 in decimal number system will give us this, right? So we can do it in both ways, either convert this into decimal, but then we'll have to convert this also into decimal, so let's not go that way. We'll convert 6 to binary string and then follow for the solution. So let's write what the question is saying. So yes, we need to find a bit string, let's say that is x, in binary obviously, and let's say x is the answer, is when added to 6, which is right now in base 10, results in this number given 1 0 0 0 0, right? So x would be 1 0 0 minus 6 in 10, right? So after doing this operation we'll get x, right? So let's write 6 as binary, and since we want to subtract it by this number and this number is represented by 9 bits, we'll have to represent 6 also in 9 bits, minus 6 in 9 bits. So signed magnitude representation of 610 will be, first of all, 6 is 1 1 0, right? But since we want it in 9 bits, and since it doesn't matter if we put zeros before any number, we can put any number of zeros that we would like. So this is what, 1 2 3 4 5 6 7 8 9, 9, right? Yes, so to take 2's complement of 6, we'll to represent it in 2's complement minus 6, we'll take 1's complement first of 610 is 1 1 1 1 1 1 1 0 0 1, right? Now to take 2's complement, we'll add 1 to this, and which will give us 0 1 0 1 1 1 1 1 1 1. This is representation of minus 6. So to get x, we'll have to add this number to this bit, right? So let's add them, 1 0 0, and here we have 1 1 1 1 1 1, 0 1 0. Adding these two numbers will get 0 1 0 1 1 1 1 1 0 and 1 carry, right? So according to our calculations, this is the required answer. So which one of the options matches? No one. This should have had been I think correct answer is not given here. Okay, yes, this should have had been the correct answer, but with this 0 bit, that is a typo here. So yeah, the correct answer should be, so this we know is, this is how many bits? 8, 9, this is 256, right? Yeah, so this represents 256, and by the calculation, if we subtract 6 from 256, we should get 250, and if you calculate this one, this correctly equates to 250, right? So yeah, an option was given wrongly, but this is the correct answer. Yeah. So let's move on to the next question. Okay, so let's move on to the next question. What is the decimal representation of 8-bit 2's complement integer? So given here is the 2's complement of some integer, and we want to find what is its decimal representation. So we know if this is a 2's complement of some number, we'll have to take 2's complement again to get back the original number, right? So let's do that. If this is the number 1 0 0 1 1 1 1 1, to take its 2's complement, first take its 1's complement. That will be 0 1 1 0 0 0 0 0, right? To take its 2's complement, we will have to add 1 here, and that will be 1 0 0 0 0 1 1 0. So this should be the positive signed magnitude of that number, right? So what does this equate to? 1 2 4 8 16 32 and 64. So 32 64 and 1 gives us 97, right? So sign magnitude representation of the positive number is 97, but since we know it was a 2's complemented number and the first bit was 1, it must have had been a negative number, which means this was actually a minus 97, right? So yeah, minus 97 is the correct answer. I hope this was easy. Now let's move on to the next question. The fractional binary number has a decimal value of, okay, so we have a binary number and we want to convert it into a decimal value, right? So let's do that. So yeah, 101.11. What are the weights of the bits? This is 1 2 4, and after the decimal ones are 2 to the power 1 minus 1, 2 to the power minus 2. Now let's convert it into decimal. We have 1 times 4 plus 0 times 2 plus 1 times 1 plus 1 times 2 to power minus 1 is 1 by 2 or 0.5 plus 1 into 1 by 4 is 0.75 0.25, which gives us 4 plus 0 plus 1 plus 0.5 plus 0.75 gives us 5 to 5.75. So this is the decimal representation, and since the number is not given in the options, the correct answer would be none of the above. Moving on to the next question. The base or radix of the number system, we need to find the base of the number system for which the following relation holds. So as I discussed earlier, for any number system x, or the weights are 1, x, x square, etc. So let's write this as expand the numbers in this radix x and try to see if we get the answer. So 312 by 20 and radix x is 13.1 radix x. Okay, so how do you write it? Weight of this bit is x squared, so 3 times x squared. This is x, 1 times x plus 2 divided by 2x plus 0, which is equal to 1 times x plus 3 times 1 plus 1 by x, right? So this will be 3x square plus x plus 2 equal to, we'll take 2x here, 2x multiplied by x plus 3 plus 1 by x. Solving this, we will get 3x square plus x is equal to 2x squared plus 6x, right? And this is a quadratic equation. We'll get x equals 0 and 5, and since 0 cannot be radix, our answer is 5. The correct answer is C. Easy. Let's move on to the next question. Convert minus 120 from decimal to 8-bit 2's complement representation. Now we're given the number of bits and we want to convert this minus 20, which must be in base 10, to 8-bit 2's complement representation. So to do that, we need to write sign magnitude representation of plus 120. That will be, let's work this out, 0 for plus, then for 120 we'll have 164, no wait, 1 yes, 164, 132, 116, 18, and that's it. This is the sign magnitude representation of minus 120. Let's take its ones complement. that will be 1 0 0 0 0 1 1 1. Taking its 2's complement by adding 1 to LSB, we get 1 plus 1 0 0 0 1 0 0 0 1. This is the 2's complement representation of minus 120. Let's see if we have an option here. Yes, B is the correct answer. Alright, let's move on to the next question. What is the maximum value of 16-bit signed integer? So this is again what we discussed in number systems. The maximum value of 16-bit signed integer. Now first of all, we need to concentrate on not the maximum, but that the number is a signed integer, which means if it is a 16-bit number, for any number, if it is a signed number, one of the bits is reserved for the sign of the number, right? So if I write say plus 3 in 4 bits, right? How do we write plus 3? Plus 3 will be 0 0 1 1, right? Now one thing that we should notice, that this 0, or let's say if you want to write minus 3, this would be more clear. How do you write minus 3? You will write it as 1 0 1 1. Now if it's not given that the number is signed and only the string is given, you could easily write it as what is it? 2 4 8 8 plus 3 11. But this is not 11, this is a signed number, and for signed number we know that MSB is reserved for the sign of the bit, so this is not equal to 11. First bit is reserved for sign of the number, and rest of the bit pattern is or represents the magnitude, right? So the first thing that we need to concentrate on that the number is signed integer, and then the next thing is how many bits it is, how many bits are used to represent the number. So for example, similar to this minus 3 example, if the number is 16-bit long, then and it is a signed integer, we need to know that this bit MSB is reserved, right? This is reserved for sign, and remaining 15 bits will be used for representing the magnitude of the number, which means this one bit cannot be used to represent the magnitude, right? If this is clear, then the answer would be clearer. So yeah, how many what now the question is, what is the maximum value of 16-bit signed integer? First thing, we have sorted that only 15 bits will be used to represent the number. So how many numbers can be, first of all, how many numbers can be represented by 15 bits? 2 to the power 15, right? If 2 to the power 15 numbers can be represented, and whose value is 32768, but the question is not how many numbers can be represented. The question is what is the maximum value of the number, and we already know that maximum value is actually maximum value of, say, n bit number is equal to 2 to power n minus 1. Just as take example of a 4-bit number. If you have a 4-bit number, how many numbers can you represent in 4-bit? 2 to power 4, that is 16. But what is the maximum value of that, like maximum value that can be represented by 4 bits? That won't be 16, that will be maximum value will be 15, because we start the numbers by 0, right? So we'll have 16 numbers, but the maximum one would be 15. Same is the case here. For n bit number, the maximum value that can be represented will be 2 to the power n minus 1. So the answer here would be 2 to the power 15 minus 1, which is 3 2 7 6 8 minus 1, 3 2 7 6 7 would be the correct answer. I hope this was clear. Let's move on to the next question. Now, what is the output of the Boolean function a plus ab bar plus abc bar? This is just for practice. Let's see. A plus ab bar plus abc bar. Let's take a common from first two terms. That will be a into 1 plus b bar plus a b c bar. Now we know that any input ORed with 1 will give us, like, what is the truth table of OR? If this is the truth table of OR, 0 plus 0 would be 0, 1, 1, 1, which means if any of the inputs is 1, then the output of OR gate will be 1. So no matter what B bar is, if there's an OR operation with 1 of any input, the output would be 1, which means this will be a dot 1 plus a b c bar. We can just write it as a. Again, taking a as common, we'll have 1 plus bc bar. Again, the same case is occurring, that this bc bar can be anything, 0, 1, whatever. B can be anything, C can be anything, but since there's an OR operation with 1, this doesn't matter, the output will always be 1, implies the result is A, which is D option here. Right, so next question is convert 557 to hexadecimal number system. Let's do this. Yes. So 557 and hexadecimal number system would be, let's keep dividing this by 60. Right. 557 divided by 16 is 34 with remainder 13, or in hexadecimal as we call it D. Dividing 34 by 16, we get 2 and remainder is 2. Dividing it by 16, we get quotient 2, remainder 2. So we'll take digits upward. The result would be 2 2D in 16. So this is equal to 2 2D, and we have an option here 2 2D. Right? So on to the next question. Fractional binary number has decimal value of, I think we have discussed this numerous times by now. 0.11 would be 0.11 would be, let's multiply it by 2. We get, no, this isn't binary. Okay. So this is in binary, so 0.11 will have, this bit will have weightage of 2 to power minus 1. This will have a weight of 2 to power minus 2. So the number will be 1 into 1 by 2 plus 1 into 1 by 2 square, which is 1 into 0.5, or which is a 0.5 plus 0.25, which gives us 0.75, right? Or 3 by 4 in base 10. So D is the correct answer, right? Next question is, how many 2 input AND gates and 2 input OR gates are required to realize this expression, Boolean expression? As we can see, there are 1, 2 and 3 AND operations going on here. So 3 AND for now, for 3 AND operations, and 2 OR operations. 2 OR operations. So number of AND and OR gates will be 3 and 2. A is the correct answer. Right? So the next question. Add 2 hexadecimal numbers. Okay, so this is just simple addition, but with hexadecimal numbers. Let's see how do we do it. 3 4 8 2 6 3 7 3 C 6 9 8. These are in hexadecimal and we need to add them. So remember that these numbers are in hexadecimal number system. So 8 plus 3 is, in hexadecimal, is 8 plus 3 is 11 and 11 is B. So we'll write it as B. 6 plus 9 is 15, or in hexadecimal it is F, which represents 50, just to remind ourselves. 6 plus 2 is 8, simple. 8 plus C. 8 plus C is 8 plus C is 12, which is 20, right? And 20 can be written as 20 in base 10 in hexadecimal is 14. Let's do this conversion fastly. So 20 written in hexadecimal is 14, so that will be 4 here and 1 carry, right? So 4 plus 3 plus 1 is 8 again, and 3 plus 7 is 10, which is 8. So this is our output from this addition operation between the two numbers. Let's see if we have the correct option here. Yes, B is the correct option. Next question. Subtract the two hexadecimal numbers. Let's try subtracting the two hexadecimal numbers. 9, 8, E, A, 9, 8, E, A, 7, F, 8, 9, F, F, 6, 3. And these are in hexadecimal number system, and we need to subtract them. So F minus 3 is, F is 15, F minus 3 would be C, 12. 7 minus 6 is 1. A minus F. Now A is less than F. A is 10, F is 15. What would that require us to take? A borrow from the next digit here. E would become D, and we'll have a 16 there, right? So since this bit has 60, we have 2 bits in 16 base number system. We'll have this bit will have 16 times more weight than this bit. This will have 16 times more weight than this one. So that is why when we take borrow, to a less significant bit, we will get a 16 there. So this will be 16. So what will be the subtraction output? 16 plus A is 10 minus F is 15, which will give us 11. 11 is B. Yes. Next one is D minus F, but D is also less than F, so we'll again take a borrow. We'll get 16 here, and the operation would be 16 plus D. D is 13. 13 minus F is 15. That will be, this was the first one, this was second one. So this will be 14, which will give us E. 7 minus 9. 7 are also less than 9. We'll again take a borrow. This will be 16, and the operation would be 16 plus 7 minus 9, just as we normally do. This will be 11 again. so 14, and E, 8 minus 8 is 0. This is the correct output after the subtraction of two hexadecimal numbers, and as we can see, option B is correct one. Yes. Moving on to the next question. Now, yes, this is the memory kind of selecting what range of memory RAM would have. So the question reads as, if chip select A15 prime, A14, A13 prime is used as chip select of 4K RAM in 8085 system, then what will be the memory range of the system? So, first of all, we need to remind ourselves how many address bit lines are there in 8085. 8085 has 16 bit address lines for 8085, right? Next thing is, we have 4K RAM. 4K RAM as in it has 4K locations in it to save memory, save data, which means 4K means 2 to power 12, which is equal to 4096. That means it requires 12 lines for addressing all of its memory locations, right? So out of these 16-bit address lines of 8085, 12 lines will be used up for the addressing of the 4K RAM, right? So if we had 1, 2, 3, 4, 16-bit lines, this is A0, A15, A3, A4, A7, A8, A11, 12, right? So if these are the 16 address lines of 8085, these 12 will be used to for the addressing of the memory locations of the 4K RAM, right? Or address for used in address for RAM, right? So remaining 4 lines, this is A14, A13. Out of these 4 remaining lines, we know that these 3 are used for chip select, right? That too in combination, A15 prime, A14 and A13 prime, which means if what all lines are used with the chip select, we specify the lines, we fix the bit value of those lines, which means if the chip select is A15 prime, for A14, A13 prime, then chip select criteria is 0 for A15, 1 for A14 and 0 for A13. Primes are for low bit, right? So we are fixing this bit pattern for A15, 14 and 13. which leaves us with this 812. What will be the value of 812? Since it's not mentioned, and we know that a bit can have two values, zeros or ones. 812 can have 0 or 1 as its value. There is no restriction on the 812 address line, which means it can have 0 as well as 1. So what will be the address range, what will be the memory range of this 4K RAM? That's the question. So for the A0 to A11 lines, these can have values from 000 to FFF, right? 0 being 000 to FFFF. There's no restriction on these lines. This is A11, this is A0, right? So they will go all through this range from 0 to all the way to F. And if 13, 14 and 15 are fixed values, they cannot have any other values. So these 4 bits can have value of 0, 1, 0, 0, 0, 1, 0, 1, depending on value of 812, right? So all of these combinations of A11 to A0 to A11 can go with either this combination or this combination, right? So what is the value of this if we convert it into a hex number? That will be 4, right? And this one will be 5. So these 4 can have value either 4 or 5, and all of this A0 to A11 can have values from 000 to FFFF, right? So first of all, because value of A12 is not restricted, we will have two ranges for same kind of for similar locations. Like if location 000, the memory location 000 can be obtained from the value of these bits as 4 also and 5 also, right? Which means all of these combinations will go with 4 as well as 5. So we'll have range of 4000 to 4FFF and 500 to 5FFF. These 3 bits corresponding to the values of these address lines A0 to A11, which correspond to the memory locations, and this 4 and 5 corresponding to A12, 13 and 14, which gives us our answer as C. I hope this was clear enough. If not, we can discuss it in next session. Yes, so that's it today for today's session. I hope I cleared some of your doubts, and meet you next week with the next week's problems. Good night. Thanks for joining.